A very good morning to all of you. Thank you for joining us. I'm Vasudha Sridharan, and on behalf of Cumulus Networks, I'd like to welcome you all to the third episode of Demystifying Networking webinar series. Presenting today will be Kelsey Hightower and Dinesh Dutt. Dinesh is our Chief Scientist at Cumulus Networks. Kelsey Hightower, otherwise known as Mr. Kubernetes, will be joining us to talk about how modern applications can be built without knowing or caring about subnets, and how infrastructure such as Kubernetes and of routing on the host can allow businesses to build applications that are cloud-friendly, agile, and simpler than the traditional ways of doing them. This webinar will be about 60 minutes, and we will answer questions from the participants during the webinar. For those of you interested, you have the opportunity to ask questions during the webinar by using the window marked questions. Simply type in your question through chat and send. You can also tweet your questions to us. Our Twitter handle is @CumulusNetworks. And with that, I'd like to turn this over to Dinesh.
Good morning, everyone. Good evening, wherever you are. Thank you for making the time to join this webinar. I hope you find this useful. So let's get started. The key takeaways I expect to get out of this webinar that I hope you leave with this webinar are that modern application design has evolved to ignore antiquated ideas for service deployment, discovery, and advertisement. One such example is Kubernetes, which Google uses, and Kelsey will talk about it as part of his presentation. And also, in order to make a pure L3 fabric so that everything is very scalable, standard, flexible, agile, we can do routing on the host. And I'll talk a little bit about routing on the host and how that makes Kubernetes deployments optional, because Kubernetes has multiple ways of deploying. So applications and servers are what I consider the last bastion of bridging. Just about, if you look at the data center networks today, everybody is considering building networks using layer 3. Everything is built over IP. Some people who have got multi-tenancy requirements think about using VXLAN, but in general, layer 3 is beginning to dominate how data centers are built. But how does bridging play a role in application design? Fine, bridging, routing. Why do the application designers care? How do they make this life? How do they change their life based on the choice that they take? So one of the things that application designers do that is very common is service or node discovery relies on broadcast. That means that when you have broadcast, they assume that all the peers are in the same subnet. Subnets do not, broadcasts do not cross subnets, and therefore the assumption is built into the application that everything is bridged, that is running within a subnet. Another example is cluster heartbeat, that is, how do I know whether my peers are alive or not, relies on multicast. That again assumes that you are within a subnet, because layer 3 multicast is seldom used. And then there are other assumptions built into the fabric configuration, the application configuration, which assumes that there is an IP subnet again. So VM mobility, as an example, continued this trend. And these are examples in how bridging is built into the fabric of how applications are designed, and as a result, hobble the ability to make applications scalable, flexible, and also very, very agile. Why is it that people look at bridging so much, and why has layer 3 not been considered in many situations? In the bad old days, IP routing was a low performance and high cost solution because that required expensive routers. In other words, if you think about today's world, what you pay for edge routers such as ASR, ISR, compared to what you would pay for a data center router is the kind of difference between an L2 switch and what you had to pay for an IP router in the past. And because the IP routers were built, were using packet forwarding in software rather than hardware, they were also slow and they had incurred extra latency. So people who wanted to design applications decided, hey, I don't want to incur that high latency. I don't have servers that are mobile because server mobility did not exist, VMs did not exist. So people tended to want to practice that design in how they build their applications. And today, if you think about it, vendors still charge extra for L3 licenses on the same box. And if you choose to use BGP, which is becoming the de facto protocol inside the data center, people charge even more than using OSPF. And also, there is no good routing protocol stack on the host because routing and switching has been pretty much a vendor specific entity so far. The final thing, of course, is that L3 has always been considered complex to configure, and L2 was always easy, though that is mythical, because it was just plug and play. But with the rise of open networking, you have merchant switching silicon that can perform bridging and IP routing at about the same performance and price as bridging. So bridging and please try using, sorry. Okay, sorry, there was a question I thought. So merchant switching silicon is making performance, latency of bridging and IP routing at the same speed. So you don't have to worry about routing and bridging. Open networking solutions such as Cumulus Linux offer routing at the same price point as bridging, so that is removed as well. So once you have all of that taken care of, what about routing on the host? Cumulus Quagga is a package that's available that we have many customers using that can be deployed on hosts, Linux host specifically, and Windows Server 2012 is also got BGP built in. There are other open source packages like Bird and XRBGP that you can use as well. All of these start to open up networking on the host as well. This siloed world where networking began, where the hosts ended, is changing with the advent of VMs and with containers. So routing simplifications, we have talked about this in the previous webinars. OSPF unnumbered, BGP unnumbered, coupled with automation, dramatically simplify L3 configuration. So with all that happening, how are modern applications designed? If I do have a network that does not rely on pure L3, what do I have to do? Are there frameworks available that will help me understand how to design modern applications and how others who are pioneers in this field are doing this? With that, I want to hand over to Kelsey Hightower, who, as people said already, is Mr. Kubernetes. Thank you, Kelsey, for taking the time to come and be with us. It's a pleasure to have you here.
Awesome, glad to be here.
With that, I'll turn over this presentation to Kelsey. I just have to start with a small switch, and we are. Can everybody see the presentation? Can you see it? Okay.
Awesome. So I'm really glad to be here, especially talking about Kubernetes networking. Before we dive into the deep end of Kubernetes, we're going to talk about what Kubernetes is. I do understand that a lot of people don't know very much about Kubernetes.
One second. It looks like there is some problem with the sharing. It looks like a blank screen. So just 1 second. I'll go back to sharing. Yes. I'll share the desktop. And I'll present.
Yep. I see the Kubernetes slide. Now I see.
Yeah, awesome. All right, so before we dive into the deep end on Kubernetes, I want to give people a little bit of overview on what Kubernetes is, some of the goals of the project, and then we'll dive into the Kubernetes networking model to talk about some of the things that need to be in place in order for Kubernetes to do what it does best, which is managing your applications. So we're going to start with a little context. The reason why Google created Kubernetes and the reason why we spend a lot of time developing it and promoting it is that Google has been using containers for over 12 years now. So containers are a big part of Google's DNA. This idea of packaging applications in a standard container, if you will, and then using automation tools to push those around our infrastructure has become the heart and soul of a Google application platform. Everything at Google runs in a container. So this is something most people don't know, that even your VMs that you run on Google Cloud Platform actually run in a container. And we're able to do this because of all the networking things that we can do inside of the containers. And we'll see how this looks for your applications that may run outside of a VM themselves. One of the biggest challenges we see with containers in general is most people have trouble understanding how to map containers to their existing tool set and existing understanding. So one of those things is, how do you deploy containers? I mean, to be honest, most containers really are a replacement for things like RPMs, tarballs, or jar files. We're really talking about application packaging for the most part in terms of Kubernetes and containers. Then once you have tons of these containers running in your environment, the next thing that comes into play is like, how do you manage all these things? How do you isolate them? How do you make sure one set of containers don't consume all the memory or CPU on a specific machine. And once you have all that stuff in place, then you have to get into updates and discovery. These are all the things that Kubernetes aims to tackle. So this different way of working requires a different set of tools, and we believe Kubernetes is that set of tools. Quick overview, Kubernetes is designed to manage containers, so all applications today in Kubernetes are required to be put into containers. This allows us to standardize the tooling that we use. We support multiple container runtimes. Today the popular ones are Docker and Rocket. Kubernetes is a project that is based on Google's experience with running containers. So we have an internal system called Borg, and Borg has taught us a lot of things about running containers in production. A lot of those things bleed through in Kubernetes with some enhancements. So now that we're basing a lot of our things on the open source world, using things like Docker instead of our own container runtime, this has allowed the community to participate, and now we have a 100% open source cluster management platform that's written in Go, and it's really easy for people to get on board and contribute. The goal of Kubernetes is to take an application focus to your infrastructure and not managing machines. And we'll see what this looks like as we jump into a live demo later on. Now, to really understand Kubernetes, we have to look at this from a very high level. So this is a 10,000-foot overview of what Kubernetes is. If we start in the middle of the stack, we have our master component. This is essentially Kubernetes control plane. This is where everything in Kubernetes is modeled and stored and persisted. Everything in Kubernetes is what we call declarative. If you want to run a set of containers, you have to declare that state. That declaration is pushed to our API server, which then stores things in etcd. And etcd is really nice to ensure that our cluster configuration is highly available and spread throughout our infrastructure. Once we have declared the containers we want to run in our infrastructure, we can have a scheduler pick that up and choose what node to run that particular workload on. Now this is where Kubernetes departs from most automation tools where static scheduling is often employed. Then we have a set of controllers that ensure that our desired state is always met. Now we're going to drill into the details of what this means. Now there's a lot of moving parts in Kubernetes, but at a very high level, the only thing you as a developer need to worry about is the API, and the API will automatically manage the entire cluster thanks to the agents that run on individual nodes that implement our policies. Now, the main reason why you would want to use Kubernetes today, given all the tools for automation that are out there, are workload portability. Now this is a very key part of Kubernetes that allows us to mimic our infrastructure in a similar way regardless if we're running on bare metal, VMs, the cloud. It doesn't matter. Kubernetes gives us a common set of APIs across storage, configuration, applications, and also networking that makes our workloads truly portable. What do we mean by portability? The main thing is very similar to the goals of Java, write once, run anywhere. So in Kubernetes model, we describe our applications and we allow the underlying tools to figure out the differences between different cloud providers, bare metal, integrations with things like load balancers, and our underlying networking stack. The whole goal here is to make a system that's completely modular and replaceable. Now, one thing we also make sure is that your applications do not have to be rewritten specifically for Kubernetes. Now this is key. So what we try to do is abstract away the network model in a way that the application doesn't have to change behavior in order to talk to other applications inside of the cluster or your infrastructure. We also avoid coupling. So when we run applications in Kubernetes, remember that scheduler we talked about. You're not guaranteed to have the same identity for a collection of processes running in containers inside of your cluster. This means you're not going to necessarily be able to rely on IP address of a specific process. You're going to instead have to focus on things like service discovery and DNS. DNS is brought into the picture so that your applications can talk to each other over standard protocols and refer to each other by names. And we'll see what that looks like in detail. The core to Kubernetes are pods. Pods are the lowest level primitive that we have in Kubernetes and represent the way we package and schedule and deploy our applications. Pods are key to understanding Kubernetes. Pods are a collection of one or more containers along with their volumes. Now this is really key here. Containers normally have sidecars or tight dependencies such as web servers like Nginx or Apache. These things need to be scheduled and run on the same node at the same time. Often these tight dependencies also need to share things like IP addresses, volumes. These are things that are classically done in VMs today, but we also mimic this behavior with a collection of containers, and pods allow us to do this. It gives you very similar semantics to VMs. Volumes. So most applications require some kind of volume, even if it's temporary file system space, usually scratch space for uploads, or maybe you're using a shared file system such as NFS. Kubernetes supports these and has native objects that we can create and share with our containers. We'll see in our pod declarations that we can create these and have them follow our workloads across our cluster. Next, once you have pods, they work like processes inside of a Unix machine. Ideally, these pods run across your cluster and can land on any node. But we need something to make sure that these pods are up and running at all times, and that's where replication controllers come in. Replication controllers are a control loop. Kind of works like your process manager on a single node. What a replication controller can do is scan our cluster through the API and determine if our pods are still running. If they're not running, we're able to create new ones based on the template and declaration we created before. Replication controllers are also what we use to scale our applications across our cluster. So maybe we start with one pod, and we're able to easily define that we would like to run, say, 4. Once those 4 are up and running, our replication controller's job will then be sure to make sure that all 4 stay running. Now this is key because even in the face of a node failure, our replication controller will create a new instance of our application even if it has to run the same server as another application. We'll talk about how that's possible thanks to isolation. Deployments. This is the primitive that most users will work with. Deployments abstract away pods and replication controllers into something that we can update, do rolling deployments, and audit. Deployments provide what we call update as a service. Things like rolling updates can be done on the server side, where we can change the version of our application and have our deployment controller ensure that they're rolled out and keep the desired count of our applications online.
So, Kelsey, one of the things I noticed with what you're doing in Kubernetes is that you have not just how you write your applications, but Kubernetes itself takes care of things like rolling updates to your application, deciding how to scale your applications. All of that is handled automatically by Kubernetes itself. So your application itself does not have to worry about things like that. Because these are things that we typically have to worry about. How do I roll out the next version of this software?
That's right. So Kubernetes' goal is to provide a complete abstraction and full management platform end to end. If we deploy your application, then we register your application with underlying load balancers. We try to give you all the controls you need to avoid logging into servers to do anything. Ideally, you won't even need extra tools. Instead, you can program to the Kubernetes API and build any automation platform you want. So yeah, that's a great point. Next, we have namespaces. So once you create all of these objects, deployments, replication controllers, and pods, we have to make sure that we have a way of partitioning our cluster maybe by organization, user, use case, security boundaries. Namespaces provide that. Namespaces give us a way to avoid name collisions in the API. It gives us a way to slice up the cluster. We can also do this by resource allocation. We can give different quotas, meaning CPU, memory allocation, to various stacks, and allow people to work with isolation around namespaces. Now namespaces are also key to doing policy enforcement. And we'll see this a little later on when we talk about some of our networking plugins. Namespaces provide the general hooks we need to prevent one set of applications running in one namespace from talking to other applications in a different namespace.
Does this namespace concept use the Linux namespace concept?
No, so that's a great question. So in this case, namespace is more of a logical partitioning inside of the Kubernetes API. So this is different than your network namespace, user namespace. This is more a way of isolating things in our API. So group A, group B, group C, that sort of thing.
Got it. So this is inside Kubernetes itself.
That's right. Now on to the meat of our demo. So with that background, one thing that allows Kubernetes to work very efficiently and abstract away all of the gritty details of managing applications is because of the Kubernetes networking model. Now most people find the Kubernetes networking model intimidating. I actually find it quite simple. So we're going to step through what the Kubernetes networking model is to make sure that we understand how simple it is underneath the covers. First, Kubernetes by default relies on Docker. So most people have some familiarity with Docker networking. So if you step through Docker's networking, normally what we end up with is each node has a private network of its own and exposes services by doing some form of NAT translation outside the machine. Now, most people see this as port mapping. Your application sees one port, and we map to a high-level port that we then need to tell other applications about. This gets really messy really fast. You no longer have a one-to-one translation for, say, your MySQL database running on 3306. Now it's presented to the other machines on port 9376. Now that caused confusion for a lot of people and also introduces the need for something like service discovery. So service discovery happens or is required when we are not quite sure what our IP and port will be. Now traditionally outside of containers, it was pretty simple. You would pick a host, run MySQL on it, and you can use the host IP to refer to that database. But in that case, you start to have port collisions. This is a big problem, especially at larger scales. And we're not just talking Google scale here. Anyone that has tens of applications can run into port issues. This is very prevalent in the Java world. If you're running an application server, most of them attempt to bind on 8080. You get the port mappings real fast in a world like that. So Kubernetes offers some solutions, and we'll see.
There's a question here. Networking applications require special policies to ensure QoS, latency, and jitter. Does Kubernetes deal with the ability to specify those parameters?
This is a great question. So one of the goals of Kubernetes is to use the underlying container platform or runtime engine such as Docker to allow us to use things that we find in the kernel API such as C groups. C groups will eventually allow us to do things at the very low levels of networking, allocating the amount of I/O a particular process can have. Now currently in Kubernetes, we don't do a lot around the networking set of C groups, but we do things for memory, RAM. In some cases, there's some ability to control your disk. But the goal of this is to be able to manage every resource in granular details as supported by the Linux kernel. So the whole goal of Kubernetes is to allow you to describe these resource allocations and enforce them. So you're right, this is the goal of our stack. Currently, network I/O is kind of tough and also is not as mature as some of the other subsystems. So as those things start to mature, you're guaranteed to find those things propagate up in the Kubernetes API to allow you to assign them to your machines. So now let's jump into the Kubernetes networking model. Now the key to Kubernetes networking model is one IP address per pod. Now this is very similar to what you get in the world of Docker, except for these IPs become first-class citizens on the network. The IP address that you get for your pod is shared with every container inside that pod. That means each container inside of a single pod can address other containers over localhost. You share ports only within your pod. So that means you can have multiple copies of your application running on a single server and avoid port collisions, even across multiple nodes. Now, one thing that we're going to talk about here today is how do we manage this kind of network. One common pattern that we see in Docker today and deployed throughout most Kubernetes installs is you start with a Docker bridge. And in that Docker bridge, we usually assign a /24 network. This gives us the ability to have 250 some odd hosts on a single machine. Now, This allows us to take a single machine and run multiple copies of our application there. But how do we actually communicate between the hosts? This is what L3 can help. Now, most people reach for an overlay network out of the box. I find this to be pretty crazy, mainly because there's a huge performance hit that a lot of people do not account for when they're evaluating this kind of technology. If you're looking for maximum speed, there are already existing tools and patterns for doing this. L3 is something that has been here well before this idea of using containers to run our applications. So hopefully we'll cover some of that in detail today.
A couple of other questions. How do you enable a view of global time? So if, for example, I wanted to do IEEE 1588 to synchronize real-time applications, is that something that Kubernetes will allow me to do?
This is a great question because it will be helpful to define where Kubernetes sits in the stack. At the very low level of any infrastructure is the physical world. This is the machines, or in some cases for people, this would be the VM. You have your network switches and routers, edge devices such as your F5 load balancers. That's the lowest level. Kubernetes doesn't do anything in that level. The next level would be the middle level. We would call this the cluster management. Cluster management sits on top of the operating systems across the host. Now, in your particular question, this real-time interface or API for global time, this would be something that's out of scope for Kubernetes. Now, you could probably see a world where there's a cluster service that provides this functionality. But Kubernetes itself, this would be something that Kubernetes would not be of concern with. Kubernetes is only concerned with deploying, giving resource allocations to your applications. What happens above that is a different set of services that you could easily deploy as a pod. For example, in Google, we published a paper about some of our real-time time services that are backed by atomic clocks and GPS. Those are quite expensive systems. But we can see something like that, which is called true time at Google, being something that you could, in theory, run on top of your Kubernetes cluster. So I think you're thinking about this correctly. Once you have a platform like Kubernetes, the very next thing you want to do is provide cluster services to your user. We already have a pattern for this in Kubernetes called add-ons. One popular add-on is DNS, logging, monitoring. We take very popular open source projects and we make them available inside of your Kubernetes cluster. So I think you're thinking on the right track of providing something like this, but this is something that probably wouldn't be shipped by core Kubernetes out of the box, but I would love to see an add-on in the future.
Another way to think about this, would it be appropriate to say, Kelsey, is if you look at real time, the machine needs to keep the real time. Kubernetes runs on top. As long as it gets a sense of time, it doesn't matter where it's getting that sense of time from.
Well, in any distributed system, so this is one thing that Kubernetes tries to abstract over. Distributed systems are hard. So we use etcd underneath, and one thing that's really hard in a distributed system is dealing with time synchronization. There's all kind of ways of doing it. In our backing store called etcd, we do this with logical clocks. So we basically get consensus from other members in our etcd cluster to manage our logical clock ticks, and that's how they synchronize time. But if you want to do something like we do at Google with true time, it's going to cost you.
Yes,
absolutely. There's physics to deal with, speed of light issues, and I think that's just out of scope for Kubernetes today.
Yes.
All right, so we're going to move along. So let's talk about the Kubernetes model. It's actually really straightforward. Once you've allocated a subnet per host, in this case, we're given a /24 to each of our nodes. If you look at this, you'll see that one node has a 10.1.1.0/24, and we increment the third octet as we go across the nodes. Now, this allows us to have all of our containers running on each node. What we assume in Kubernetes is that each of those containers can talk to the other containers on the other nodes. Not only can we talk to every other pod running inside of our cluster, we should be also able to talk to every host running in our cluster. This is key to understanding the Kubernetes networking model. Notice we don't enforce how you propagate these routes. We actually don't even enforce that you use L3. You're free to bridge your primary interface and put this bridge on the network. But as mentioned before, that is not the scalable solution. Great for demos, going to wake you up in the middle of the night for production.
Yes.
So let's talk about network isolation really quick before we jump into our live demo. There's going to be a few other objects that I want you to understand, but the key to understanding Kubernetes networking model is not necessarily the network topology, because you're free to implement what you need, but you have to understand how we do network isolation. Now, network isolation is this ability to have pods talk to each other. Now, what's coming in Kubernetes 1.3 is the availability of using a network or a namespace to actually control which pods can talk to which other pods. Now, this is easier to do in a network namespace, mainly because we can have containment based on application boundaries. Now, within each pod itself, we're also using the network namespace functionality of the Linux kernel. This what allows us to have one IP address or one networking stack per container group. We expand that scope a little bit across network namespaces or Kubernetes namespaces. Now, there are currently a few projects implementing some of this functionality today, such as Project Calico, which allows you to have network policy be driven by namespaces. This is really handy for people looking for more granularity than what's provided by Kubernetes out of the box. Now, most people will be thinking, hey, I already have a networking solution that I would like to use to do these things like IP management, things like firewall implementations. All those can be added to Kubernetes via network plugins. We're using a standard network plugin interface called CNI. Now, this was invented at CoreOS about 1.5 years ago. And what CNI does is provide a very simple interface to allow container runtimes to execute inside of a network namespace and configure the network stack. So ideally, if we're creating a container, we can hand it off to a CNI plugin, and it's free to create the network interface, give it an IP address, and once it's complete, hand our container back to us, and then we can register it with the rest of the Kubernetes stack. Now, I must warn you, this is more than bleeding edge. This will probably get you fired if you do it wrong. So take that caution, but know it's coming. The idea here is that we should be able to support any of the existing networking solutions that you trust today and have it be a first-class citizen in the Kubernetes API going forward.
Question here. Do we want to take that now, or
I'm looking at it.
Cool.
Okay.
So now that we have IP addresses for all of our pods, we have all these things running in our cluster, how do we get them to the outside world? Now, this is where most people trip up in Kubernetes. Now, by default, you can actually do a lookup of every pod IP inside of the cluster. We have a grouping construct called labels, and labels allow us to query for a set of containers by a specific set of attributes. Now, these services could be automatically integrated into your load balancer of choice. Let's say you have F5. Nothing's stopping you from monitoring the Kubernetes API, grabbing those IPs of pods as they come and go, and updating your backends dynamically. The truth is, most people don't have access to these kind of APIs. It's still a dream come true, right? All this talk about SDN has resulted in more like spreadsheet-defined networking than true automation. So let's talk about services. Services is a way to abstract some of this and kind of give you a very easy mode to operate out of the box. Now keep in mind, this is just the easy mode. You can bypass some of this functionality if you want to have maybe more performance or do something in a slightly different way. Services are a group of pods that work together. So you can imagine have a copy of your front end. Maybe you scale it from 1 instance to 5. Now, all 5 of those will be considered a single service in Kubernetes. But how do we abstract that? Well, networking, of course. We can use a virtual IP. Now, this virtual IP is pretty special. It's not necessarily routed throughout the network, but we use a few tricks on the native OS to make it seem that way. When a virtual IP is allocated for a service, we actually update IP tables that will intercept traffic going towards that virtual IP and round robin across all the pods that make up that service. Now, I know you have a few questions. One of those questions is like, what pod am I going to actually route to? Well, this is where the API server comes in and another tool called kube-proxy. So kube-proxy listens to the API server on every single machine. That's right. If you had 1 million machines in your cluster, this would be kube-proxy listening to the API server and managing our IP tables rules to ensure that this virtual IP is configured on every single machine. What do you get when that happens? You get the ability to reference any other service in the cluster, even if that service is not running on the same machine as you, and you will be forwarded to the correct pod running within the cluster. Now we're going to talk about how IP tables work. This is going to drill down a little bit into that workflow that we just talked about. So we have kube-proxy running on every single machine. Kube-proxy interfaces with the native net filter, or IP tables if you're a sysadmin like me. Now the API server has all the definitions of services. Again, services are just an abstraction across a group of pods that make up a similar set of functionality, and we mimic that with an IP address. So the kube-proxy watches the API server on services and endpoints. That retrieves a list of the pod IPs that make up our service. We call kubectl run to create a pod. Our scheduler places those workloads on our cluster in the right place. Once those pods are up and running, that means they now all have an individual IP uniquely identifying each pod in our cluster. Now we choose to expose our service to the rest of the network. So we run the kubectl expose command. Don't worry, we'll be given a live demo where we type these commands out so you can really see what's going on. The kube-proxy sees that there's a new service online, and it starts to configure IP tables. Now, there's a bit of magic that happens here, and we'll do a dump of the iptables rules to really show you what's happening behind the scenes. For those of you with iptables experience, you'll see that there's no magic happening here. These are just standard features of iptables that we leverage inside of Kubernetes. Now we take that VIP, and we make that VIP available on every single machine. Anytime there's new endpoints, we scale our nodes. Kube-proxy will get an update. Again, we cycle through and we update iptables again. Now, any of our clients that choose to interact with that virtual IP will go through the VIP, and then, by luck of chance, through some random algorithm inside of iptables, we'll find one of our pod endpoints. Now, this happens somewhat at random, but the idea here is to give a chance that every pod will have even distribution of our traffic. Now this works even if the pod's not running on the same machine. For a lot of you with networking experience, you'll see that there's also a drawback. One of the drawbacks here is that you're going to have to pay double hop. If you land on a machine that doesn't have the pod running, or even if it does, there is no guarantee that you're going to stay on the same machine. But again, this does provide the flexibility of not having to worry about any of that. Lastly, external services. External services allow us to integrate with things like load balancers. This is great when you're running in a cloud environment. But remember, cloud doesn't always mean a hosted cloud provider. You can actually have a cloud on-premise. If you had a nice API or API access to something like your F5, there is no reason why we can't provide a cloud provider for bare metal environments where we orchestrate load balancers, even in that scenario. You also have the ability to do it yourself. HAProxy, Nginx. A lot of these tools provide APIs to dynamically allow you to update backends. We're going to skip over the ingress controller because we're going to get to the live demo, and we'll see how Kubernetes works in action.
Okay. While Kelsey is switching over to the live demo, a couple of questions that were asked. Kelsey, meanwhile, while we are doing that, I also will turn off. I had thought I had turned off my chat account, but looks like I had not, and I apologize for the distractions that were there. Questions. First is multi-tenancy. How is multi-tenancy handled inside Kubernetes?
So this is one of the things that most people are having challenges with today. So one thing we do in Kubernetes, we do expose some of the security constructs that you find in Docker today. Things like SC Linux, and some of the other things that allow you to limit system calls between containers. These are network namespaces are not quite plumbed through to the Kubernetes API. So as it stands today, multi-tenancy, where you want to run untrusted applications for multiple users, I would say that's something that's not quite supported today. This is why in most Kubernetes cluster setups, most users have their own clusters per organization or security boundaries. So the idea here would be whatever you're doing today to run your applications, many people are using RPMs or maybe jar files, and you're dealing with multi-tenancy in a way that works best for your infrastructure and your organization. That may mean partitioning where applications can run. Kubernetes offers support there by saying, hey, only run these pods on specific machines that match a set of criteria. That will influence our scheduler to avoid certain machines inside the cluster. So this is one way of sharing resources, but preventing machines or applications that can't live on the same server to not actually live in the same place, therefore retaining your security policies. So today, Kubernetes isn't the holy grail that you're going to build your cloud provider on, but it's a great way to manage your applications with a little bit of better automation tooling than what you may have experience with today.
The second question is, for cost reasons, we would like to migrate critical infrastructure applications to the cloud. Would it ever be possible to create policies to ensure that real-time applications can be synchronized? Ever, what I've realized, is a very long time, but
yeah, I mean, so, when it comes to, again, this application layer, what you really want out of Kubernetes is to give you an easy way of deploying your applications. So if you want 20 copies running and they need to run in specific availability zones, if you want to ensure that these applications are always running and even in the face of node failures, applications have the correct configuration, that maybe there's automatic load balancers being updated, that's the job of Kubernetes. It's going to manage and orchestrate those things. When it gets to the application layer, that is just not the right fit for Kubernetes. Now, many people are starting to build their platforms on top of Kubernetes. We see this with OpenDAS, OpenShift. Many of these cloud providers or platform providers are starting to use Kubernetes as a lower level orchestration platform in order to give you these kind of services. So I would imagine in the future, some vendor, or maybe even yourself, will provide things like this through cluster add-ons. So with that question out of the way, we're going to jump in and see what it's like to deploy an application in Kubernetes and take a peek at some of the networking infrastructure underneath before we hand it back off to really look at how we can manage L3 routes on the host.
So here in this, the network topology, just to give a quick update, is there are essentially 4 hosts connected in a 2x2 class to the rest of the network. So the 4 hosts are connected as a class in a class network. The class network running on top is essentially running Cumulus Linux, and they are all VX based right now. So let's get started with the demo, because we have a few more things that we need to dive through.
All right, so what we're going to do here really quick is we're going to actually run a pod. And here what we're going to do is just use Kubernetes in what I call easy mode. We're going to call the kubectl run command to create an nginx pod. Now what we're going to do is take a peek at what happens in terms of IP allocation on this machine. So what I'm going to do is call kubectl run nginx image equals nginx, and then we want to have that port advertised, port 80, as an inbound port for the application. Now when we run this command, we get one of those deployments we talked about. Now the deployment will create what we call a replication controller. And this replication controller will allow us to grow and shrink the number of these pods running, but it also has a template. Now once we have our pod in place, we can actually see what pods are running. We have 1 copy. The reason why we only have 1 copy is because that's all we told our deployment controller. So by default, we only get 1 copy of our pod. We see that we have our nginx pod. Now let's look at our nginx pod really quick to see what its networking IP is. We can use the describe command to see what the individual IP address is. We'll just scroll up here. And we see that our pod IP is 10.100.21.2. So our pod has a unique identity, and what we can do, we'll just run curl to make sure that that works. We see we have nginx. The thing is, we do not want to give this IP address to any of our consumers. Reason being is that this pod could die and be rescheduled to a new machine. This IP address becomes useless. What we need instead is a service. So in order to get a service, we'll run that kubectl expose command. So we're going to expose our deployment called nginx. And by default, we're going to get a cluster IP. Remember, that's that VIP that allows us to abstract away the underlying pod IPs. Now that we run that command, we can actually check that out. And we see that we have a cluster IP here. So if I wanted to, I can run curl on that cluster IP, and we get nginx. Now how does this work? Well, let's take a look at iptables really quick to get a quick glimpse of what's going on underneath the covers. I'm running the iptables save command to give us a dump of what's going on underneath the covers. Here we see a collection of iptables rules that intercept traffic and move it around iptables, and now allows us to forward things to the pods underneath. Now, this is all being maintained by our kube-proxy. Again, it listens to the API server, gets our configuration, and updates this. Now what happens when I scale the number of pods? So let's get that service one more time. We're going to describe it. So we can see all the endpoints. Here we see that we only have one pod. Now what I'm going to do is scale it. So we're going to run the kubescale deployment command, and we're going to scale the deployment called Nginx. We're going to bump the number of replicas. So notice what happens now. If we describe the service, once these pods become healthy, they're added automatically to our endpoint. If you're managing a F5 load balancer, you can watch that endpoint and you'll see these pods come and go. Then you would update your backends dynamically. Let's scale that back down to 2 and see what happens. And as soon as it goes away, we're down to 2. You can do dynamic configuration of your upstream network devices using this simple API. If we go have a look at our iptables rules, we'll see that we're using some native functionality in Kubernetes to share the load across our machines. This is a lot of output, so let's call grep to filter it out a little bit. So here, you notice that we're getting an iptables rule to do random probability of sharing the load. Let's add a few more backends to see what that looks like. So once those pods come online, in almost real time, we actually get new rules put into iptables. So at this point, I can use that cluster bit to round robin across all of those nodes. And with that, I would end this Kubernetes presentation, and we'll see what it takes to make sure that all of these pods can talk to each other across the multiple machines.
So if I ran kubectl, the curl right now, what it's going to end up at one of these pods at random, right?
That's
so
right.
Now I'll run curl on the service IP.
Exactly. So if we take the service IP address here and we call curl, what will happen is this IP address will be intercepted by my local iptables entry. So if you look at our entire iptables output here, we'll see that there's a role for this cluster IP. Right, here we go. Right. So anything that's targeting this IP address will go through a new chain, which will then catch the random probability of going to any of the other pods underneath. Yep. So we hit this cluster IP, and we're automatically bounced over to the actual service implementing the pod.
And now you've essentially got a cluster IP whose IP address is completely isolated in one sense from the pod IPs.
That's
this
correct.
cluster IP has no connection, no bearing to the pod IPs. The pod IPs can be in completely different subnets, and there's no connection associated with that.
That's exactly right. And if you have routes in place, then you can expand over the normal boundaries that L2 limits you to.
Exactly. So before, let's get back on, to get back to where we were. So what Kelsey showed us is essentially a way to scale applications dynamically to work with whatever workloads you have. Once you have a platform, you can use Kubernetes to scale applications, to do rolling updates, all completely independent of what the IP addresses are. You can have service IPs which are WIPs, and you can proceed with that. So what is T for the Tillerman? So Kubernetes is the helmsman, also the Tillerman, and the way that if you want to run things on-premise, not inside the Google Compute Engine, but if you want to build a complete network inside and use Kubernetes as your cluster manager or as your platform to deploy scalable applications, one of the things you will need is the ability for all of the different machines to be able to talk to each other. One way to get them to talk to each other is to use layer 2 and build overlay networking. But you don't have to use it that way. You can use just a pure L3 network. And the way you do that is you essentially run a routing protocol on the host. So routing protocol on the host, isn't that complicated? What if the configuration could be as simple as this? You have an EAT0 interface, and all you do is simply say, I want to peer with my neighbor on EAT0 and just distribute my connected routes. When Docker has its connected routes and things come up and go down, all that will happen is essentially those routes get automatically advertised to the outside world and everything just works. In reality, with 3.0, what you have is a few more lines. You will have to announce, this is thanks to PowerPoint, it made the router capital, it's really small r, router BGP, and you have a router ID, which is about the only thing that changes across every machine. But other than that, the rest of the configuration stays identical across all of the machines. There is nothing fancy going on there. Essentially, you're saying, I want to peer with my neighbor, my BGP neighbor, on the interface each 0. I don't care what his AS number is or any of that stuff. Just distribute, announce the routes that I have connected, routes that are up. And today you can get into some more details on this. There are two ways to use BGP on the host. You can use something called dynamic neighbors, or you can use BGP unnumbered. Essentially, when you think about BGP, for those who are versed in this, there is something called autonomous system number. All the servers just use a single ASN, and that's about it. So with BGP on the host and dynamic neighbors, all you can do is configure the TOR, that is the leaf switch, to be the subnet to which the clients can connect. All the clients are connected via a bridge on the switch itself, and once you type this command, as the servers start connecting, the BGP connection establishment happens, and then from there on, it's just regular BGP. If you don't want to do that, what you can do is run BGP unnumbered as the example configuration I showed you, and essentially run a pure L3 network, which is completely interface based. There is very trivial configuration on the host and on the switch, and it's pure L3. There is no bridging involved anywhere except for the Docker IP bridges under which all containers within a pod run. And as for the OSPF aficionados, there are other ways you can do it with OSPF as well. Of course, you have to do some seat belts with routing on the host. Hosts are always stub networks. You never want them to be transit. So for example, if you are in OSPF, you now make the host essentially stub networks. In case of BGP, you only announce the default route to the host. There's nothing really going on the host. And you only accept specified prefixes from the host. So for example, in the case of Docker, as Kelsey pointed out, if you've got Docker IPs coming out from a particular pod and he gave you an algorithm of how every node has a IP that is incrementing, IP subnet that's incrementing, you can only accept those specified prefixes from the host and thereby prevent any malicious routes from being injected. So if you look, we are actually out of time. I was hoping to show a little more on what was going on the routing side of things. But I will put up the playbooks that I have essentially to build N by M clause and deploy Kubernetes across the entire host configuration and be able to test out Kubernetes. So I will put out those instructions on the Cumulus community webpage so people can use Vagrant, the Cumulus VX, and Kubernetes available binaries and etcd available binaries to be able to take and configure this and play with it themselves so they can actually see what's going on. A real-life deployment will look a little different from what you do in Vagrant because of certain vagaries of Vagrant, so to speak. And so we'll talk about that. I'll make a note of that in the README that is going with the deployment, the Ansible playbooks that I'll be putting out. So we have other real-life examples. This is not as Kelsey pointed out, routing on the host is not just a Kubernetes use case. We have a customer who's running routing on the host, doing container networking, but they are a very advanced customer and they have done everything by themselves. What Kubernetes does, they have built it by themselves, and they're a mid-sized customer and doing it with OSPF. They're planning to move to BGP. Another small to mid-sized customer is running with BGP unnumbered. We have a large customer who's running with BGP unnumbered with routing on the host. We recently announced a 300+ OpenStack cluster with VXLAN and routing on the host to build an OpenStack cluster with L3 rather than with L2. And then many other customers are in POC or in pre-production. All of them, the majority of them, are now switching to container-based applications. So to sum up, building pure L3 fabrics is real. Network, compute applications are all showing how to do this. You do not need to rely on bridging standards. Mechanisms for service discovery, service health checks, and for automatic scaling and rolling updates. All of those things which are considered application management are being handled by frameworks such as Kubernetes that allow you to deploy these. And since this is what Google has been using for lots of years, this is a well-tested model. This is not something that is immature that's just been thrown out. High-quality open source routing stacks are available. Cumulus Quagga is one of them that we have used as part of this demo. All of the networking that was set up for Kelsey to do what he showed today was running off of a laptop with Vagrant, and all of the networking was done by Cumulus Quagga running on those hosts as well. With that, we come to the end of this webinar. If there are any last-minute questions, I'd like to take them now. Thank you, Kelsey, for taking the time to be here. I hope for all of you who are here, you learned something about how building pure L3 fabrics and applications will actually make your network scale well, your application scale well, and this is how the modern data center is progressing. So this is how people are building applications today and building their networks to serve those applications today. Thank you very much. Wish you all a wonderful day. Bye-bye.
And thank you, Dinesh and Kelsey as well. And thank you again, Kelsey, for joining us.
Thank you.
A wonderful time today with you in this webinar. We would love to get some feedback from the follow-up emails, and also feel free to send us suggestions about other topics that you want to hear about in this webinar. And do tune into our next webinar on May 26th. Details will be available soon on your website. Thank you, everyone, for your time today.